pleasure to welcome all of you to the Fall 2014 Margaret and Herman Sokol Science Lecture. This lecture is presented by the College of Science and Mathematics as part of the Sokol Lecture that was established in 2002 through a generous gift from benefactors and MSU alumni Margaret and Herman Sokol. The annual lectures provide an opportunity for members of the university and surrounding communities to gain a greater appreciation and expanded knowledge of important issues in science. Tonight, I am especially pleased to welcome Dr. Maureen Raymo. Dr. Raymo is a Lamont Research Professor and Director of the Core Repository at Lamont Doherty Earth Observatory of Columbia University. Dr. Raymo is a Fellow of the American Geophysical Union and the American Association for the Advancement of Science. She's been recognized for her cutting-edge work in paleoclimatology and paleoceanography in an array of venues. In 1992, just 3 years after obtaining her doctorate, she received a very competitive Presidential Young Investigator Award from the National Science Foundation. And in 1993, she was appointed Cecil and Ida Green Career Development Chair at MIT. In 1994, the Joint Oceanographic Institutions named her a Distinguished Lecturer at Montana State University. And flashing forward, this year, Dr. Raymo became the first woman in the 183-year history to receive the prestigious Wollaston Medal, the highest award of the Geological Society of London. And just as a reference point, the Wollaston Medal awardees include Charles Darwin, Louis Agassiz, Sir Nicholas Shackleton, and James Lovelock. Good company. Also this year, she was awarded the Milankovic Medal at the European Geosciences Union's annual meeting for her use of geochemistry, geology, and geophysics to solve paleoclimatology's big problems. This medal is reserved for scientists who have successfully pursued outstanding research in long-term climatic changes and modeling. And in 2002, she was included by Discover magazine in a list of the 50 most important women in science. While born in California, Dr. Raymo spent her formative years in Easton, Massachusetts, watching, and this is one of the only things we have in common, Jacques Cousteau on TV, stimulating a deep desire to explore the world. She was also clearly influenced by her father, a college physics teacher and popular science book author, and her mother, who was a teacher of children with learning disabilities. In fact, Dr. Raymo wrote a popular geology book with her father entitled Written in Stone, A Geologic History of the Northeast United States. Two things I should point out here. Number one, our own Jack Isidore, Dr. Jack Isidore in our chemistry department, actually had his first class in physics with Dr. Raymo's father. And I should also note, while not here at Montclair State, Dr. Raymo's son is also coincidentally majoring in geology. Dr. Raymo received her BS in geology from Brown University, attended graduate school at her current home, the Lamont Doherty Earth Observatory of Columbia University, where she earned a Master of Arts degree in geology, a Master of Philosophy degree, and a PhD. She accepted simultaneous positions as visiting research fellow in meteorology and associate scientist in geology at the University of Melbourne. Then, in 1991, she moved to UC Berkeley as an assistant professor, but was lured back to Massachusetts and accepted a position at MIT. She remained there until 2000, when she moved to Boston University as a research associate, ultimately returning to Lamont Doherty in 2011. Dr. Raymo has become a common face and voice on TV, radio, and in film, discussing climate change issues. Her distinguished career in groundbreaking science means she is also a highly sought speaker, and we're lucky to have her here with us tonight. Discussing collapse of ice sheets in the ancient climate and what this means for the world now, it's my great pleasure to welcome Dr. Maureen Raymo.
Thank you for that introduction. I might set a record for the longest introduction I've ever had. I hope I can live up to it. Anyway, thank you very much for being here. It's a great honor. And I actually, hearing all that, it reminded me of how long I've been doing this. And in fact, I started studying past climates when I was in spring of my freshman year in college, which was 1979. And the study of past climates was a very esoteric little sidewater of the geological sciences. And, but I found it fascinating, and I was out working on deep sea cores and looking at how the animals in ocean sediment changed through time. And now fast forward to 2014, and now I'm in a field where I go to a party anywhere and people have all these questions they want to ask me all the time. So it's been a real transition over the course of my career. And I am happy to stay here at the end of this talk as long as anybody has questions. And I hope you have a lot of questions at the end, because the topic that I'm going to talk about raises a lot of questions. So let's see, I should start my timer so I have an idea of how long this is going to take. There we go. And I'm going to start my talk with the first half of my talk, first third of my talk, talking about really kind of where the state of the art we are in the field of climatology and climate change right now. Probably this light up here is really bright, so if I'm squinting, that's why. But I'm going to talk about what we know about recent climate change and what we think what's going to unfold in the coming years ahead. And really, this is not so much my research, but really the collective wisdom of 30 years, my entire generation of climate scientists, the net result of all the polar glaciologists and the tree ring people and the oceanographers and the satellite people and the climate modelers sitting behind computers. But we'll start with this record right here, which is probably one of the most famous data sets in the geological earth sciences. And this, of course, is the record of atmospheric CO2 measured in the atmosphere on Hawaii, started in the late 1950s, and has been measured continuously ever since. And now, of course, there's stations all over the world measuring CO2, and you could Google every day's value at co2now.org. And here we are at 397 parts per million. So in just the time I've been alive, atmospheric CO2 has risen by about 30%. And right now, this is an annual cycle. All these little things are annual cycles. During the spring, all the trees in the northern hemisphere leaf out. That's where most of the trees in the world are. Leaf out and draw down CO2. In the fall and through the winter, all those leaves start decaying and releasing their CO2 back into the atmosphere as they're oxidized. And so by next spring, we'll be up over 400 parts per million. But superimposed on this annual cycle of the Earth breathing in and out, the biosphere breathing in and out, we have this long-term trend. And this long-term trend is the combustion of fossil fuels by humans, okay? So we burn fossil fuels, and CO2 is a byproduct of that. Now, so this is the root of, you've all heard, I'm sure even in high school and grade school, that CO2 is a powerful greenhouse gas, and its role in the atmosphere is to trap the Earth's outgoing radiation near the surface and preventing all of the Earth's, some of that radiation from escaping to space. And the reason the mean temperature of the surface is above freezing is because we have this layer of greenhouse gases that keeps the surface of the Earth warm enough so we have liquid water. Now, if we had no atmosphere, the mean surface temperature of the Earth would be below freezing. So, but now we have this greenhouse gas that's critical to maintaining the Earth's temperature balance, and it's increasing. And I want to, as a geologist, I'm always thinking on long time scales, and that's one of the hardest things to do for people that aren't geologists, really stretch their minds over these long time scales. And here's a perfect example. I just showed you a record that went from the 1950s, and that is that red line right there. So now I'm putting these instrumental measurements within the context of measurements that go much further back in time that weren't made with instruments, but were made by looking at the composition of air trapped in ice bubbles in ice cores. So snow that got eventually turned to ice in the polar ice caps. So doing that, we can extend the record of atmospheric CO2 back through the Holocene, 10,000 years. So here's today, here's 10,000 years ago. And you can see that during this warm period of the last 10,000 years within which human culture and agriculture arose, CO2 was about 275, 280 parts per million. Then a very gentle rise started. It was probably the early deforestation. And then, as you can see in this blow up, by the mid-19th century, this very pronounced increase, which is the Industrial Revolution. Okay? So, what's this going to do? Let's look at this in terms of temperature now. It's a greenhouse gas. You would expect it to increase the surface temperature of the Earth. So starting in the 80s, when people started paying attention to this record, there were a bunch of hot summers in the 80s. They're like, well, wait a minute, has this been warming Earth's temperature? So for decades, even as recently as the last 5 years, large research groups have been trying to reconstruct Earth's surface temperatures over the last 1,000 years to see if there's a signal of warming in this temperature record. And so here you have northern hemisphere surface temperature from 1,000 years ago to today, well, not quite today, to the early 2000s. And in red are instrumental records of temperatures. These are from hundreds of weather stations all over the northern hemisphere. And in blue are what we call proxy temperature records. So these are temperatures inferred from things like ice cores, isotope ratios in ice cores, tree ring records, isotopic proxies in coral bands going back in time. And so the light gray is the error, the estimated error on these reconstructions. But group after group after group have done these reconstructions over the last 20 years, and they all look remarkably alike, and you may know, some of you may recognize this as the hockey stick. So when you hear, there's the hockey stick, that's it. So, you know, it looks like a hockey stick. But this is real, and if you come here to the late 20th century, and go look back in time, you see there's been no time in the last 1,000 years as warm as today. And furthermore, you see that while there's this natural climate variability that's continually operating throughout climate, there has been a pronounced and steady increase superimposed on this natural climate variability over the last 150 years, okay? So, here's another way to look at it. And what you're looking at now is this same data reconstructed from around the world, except we're just stepping through time now. So we'll just watch it. It'll come up to the present. You'll get a sense. You're looking at an anomaly relative to the average temperature between about 1950 and 1980. So it's much, you know, it has a much bigger impact when you look at it this way than on an XY plot, doesn't it? And, you know, I don't know if there's any gardeners out here, but, you know, if you've been gardening for 30 years, you notice this. These changes are now of a magnitude that people are starting to notice it in their lives. I mean, these are tiny anomalies. Up here, 2 degrees warmer than the average from 1950 to 1980, I think is the average. In other places, not so much, but you get a sense that the global mean is changing, okay, from year to year. And you may also have read recently that NOAA just declared 2014 the warmest summer on record. Okay, so coming back, so speaking for 97% of scientists that study climate as a living, we all are very comfortable with the hypothesis that the increase in atmospheric CO2 through the known combustion of fossil fuels, half of it's in the atmosphere, half of it's gone into the ocean and into the biosphere. The half that's remained in the atmosphere has resulted in a warming of the Earth's surface temperature over the last 100 years. Now that's great, and it's a nice confirmation of theory, et cetera, but the real scary bit is there's no sign that we're gonna run out of fossil fuels anytime soon, and every year we go forward, the combustion, the utilization of fossil fuels is increasing, okay? The rate at which we are putting CO2 in the atmosphere is at an all-time high. I like this figure for a couple reasons. It came out in an IPCC report back in the late 90s. And again, think about your time scale here. Here's today, 2014. Here's 1,000 years ago. We're looking at CO2 again. Here's the ice core data coming along around 280. Here we are getting in the mid-1800s, starting to go up from the Industrial Revolution. Here's where the instrumental record in Hawaii began, and going up, and of course now we're at 2014. But why I like this figure is because in the 1990s, lots of different climate modeling groups were starting to try to predict how warm it's going to get in the future. So these are huge, complex models of the Earth's climate system that you hear these predictions. They're used to predict what will happen in the future. It's the same models that we use to predict weather, and they're getting better and better, right? I mean, I never used to believe the weather reports when I was, a college age, but now the weather reports are almost always right. These models are getting better and better and better. So, but what they wanted to do, they said, well, look, if we have all these different groups predicting future climate change, that's fantastic, but we need to all do the same experiment. So they said, so let's create a series of scenarios of how CO2 might play out over the next century, okay? And we'll call one of these scenarios, for instance, this black one, the kind of business as usual scenario, and then we'll have scenarios where there's rapid transitions to renewable fossil fuels and increases in efficiency and stabilization of populations. And then we'll have kind of really fast growth, high consumption scenarios that, and in those scenarios, by the 2100 would have an atmospheric CO2 level of over 900. By comparison, here we are at 400 today. Okay, but what I like about this is that even at this time, right now in 2014, the rate of CO2 increase, I shouldn't say I like this, but right now the rate of CO2 increase since this figure was made has been faster than the worst case scenario. So if you're asking what trajectory we're on today, we're up here on this trajectory, okay? So then you start to ask yourself, okay, this little bit has resulted in the warming you just saw. What's going to happen over the next 80 years? What's likely to happen? Okay, so, the simple answer is that obviously it's going to get warmer. I mean, really, the physics is so clear about that. There's really nothing else that could happen if you let the CO2 continue to increase. Anyone know what the surface temperature of Venus is? It's incredibly hot. You would die in a second. And Venus's atmosphere is filled with CO2. Nothing can escape the massive CO2 clouds of Venus. It's so hot it burned off all Venus's oceans. It's like a cauldron. Okay, that's not going to happen on Earth, but I'm just saying, CO2, don't worry. CO2 is important, though. You know, that's always been the great thing about Earth. You know, it's the Goldilocks planet. Mars doesn't have enough, Venus has too much, and Earth was always just right. So that's why life arose on Earth with its nice oceans. But now we're playing with that little dial, and it's going to get warmer. The Earth will survive. Some bacteria will probably love it, but it might not be. We'll talk about what that could happen for us. But anyways, the point is, getting sidetracked here. So here's some variations in Earth's surface temperature predicted from basically 2000 out to 2100. And you can see that black business as usual line has a temperature about 2 degrees Celsius on average warmer. By comparison, that figure that the movie I showed you has about a 0.7 degree warming over this interval right here. So, you know, take that and like crank it up by 3 or 4 times. But again, there's a huge range. I mean, this range is highly uncertain. But even the best case scenarios have Earth's surface temperature increasing by another degree Celsius, okay? And that's only if we take very dramatic action in trying to restrict the increase in atmospheric CO2 over the next coming decades. Okay, however, I'm very interested in sea level, and I'm going to talk to you about sea level for the rest of the talk. And you might think, well, the Earth's surface temperature has been increasing. What has sea level been doing? It, too, has been increasing. And sea level is a lot harder to measure than Earth's surface temperature, which I think at the end of the talk, looking back, you'll appreciate just how difficult it is to measure sea level. But for now, let's look at this record going from the late 19th century to the present. And this is the trend in sea level based on tide gauges around the world. And this is the trend in sea level from satellite data, which has been collected more recently. And basically, there's been a steady increase in sea level of about 3 millimeters per year, or 30 centimeters per century, over the last century. And the source of that rise in sea level is twofold, primarily. About half of it is due to thermal expansion of the surface ocean. The 70% of the ocean, of the Earth that's covered with ocean, has been absorbing heat all through the last 100 years, and it's expanding thermally. And that's enough to impart a significant, noticeable rise in sea level. And the other half of it is due to the retreat of mountain glaciers around the world and polar ice caps, primarily West Antarctica and Greenland, and possibly some very poorly constrained component from East Antarctic ice sheet, okay? So again, this is likely to continue, and let's just put that in a longer context. I just showed you a 100-year record, and right there is the 0.3 millimeters, the 3 millimeters per year rise in sea level. And now this is a long sea level estimate. This is an estimate of sea level rise on the North Carolina coast based on marine sediment in marshes, coastal marshes. This is by Ben Horton's research group at Rutgers. And you can get a sense of how that recent sea level rise compares to the natural rate of sea level rise over the last 1,000 years. And you might also think to yourself, well, yep, there's the hockey stick again, right? So it's coming into play. So where are we going to go with sea level? Here's tide gauge data and satellite data right here, some of the more historical reconstructions right there. And like the temperature predictions, the predictions of sea level for the future span a large range with a large uncertainty. We don't know how warm it's going to get. How high the CO2 gets is going to depend critically on the choices society makes over the next decade or two. So how high will sea level be? Generally, the low estimates come in around 0.5 meter, roughly. High estimates come in around high mid-range estimates come in around 1 meter, and there's many scientists within the community that feel very comfortable with the possibility that up to 1.5 meters to 2 meters of sea level rise could happen over the next 100, 120 years if absolutely nothing is done to rein in global greenhouse gases. So what does this mean? Greater than 3 feet, 1 meter. Let's try to put that in a social context. This is a map that shows the population that lives below 4 feet in the US relative to sea level, within 4 feet of sea level. Almost 5 million people, and most of those in Florida. In addition, is shown nearly 300 energy facilities, and these would be nuclear power plants, oil refineries, gas ports, natural gas ports, et cetera, that are within essentially 1 meter of sea level. So these now automatically all become at risk. I don't have to explain to this crowd what the potential for even a small rise in sea level can do to the severity of a storm. Sandy obviously was so devastating because the storm surge hit at high tide. Typically, that would be an anomaly. So you raise sea level by a few feet, obviously every storm surge is going to be the equivalent of now being at high tide, and ones that do happen to hit at high tide will now be even more devastating, right? Florida, this is the land mass in Florida within 1 meter of sea level today. And here's the lower east coast, the east coast of the upper Atlantic states. Again, significant amount of real estate, much of it with very expensive houses at risk. And here's another one from East Carolina University. Anything that's orange to red, again, is within 1 meter of present-day sea level. Okay, so this is more, there are many groups around the country that are seriously concerned about the impact of even the minimal sea level projections. At the same time, there are state governments, as in North Carolina, that in 2011 wrote it into the law of the state that predictions of sea level rise in the 21st century can only assume the same rate that has been observed historically. That they made it illegal to predict sea level rise as accelerating, even though that's what it's doing. So, you can imagine if you were building a bridge that you wanted to last 100 years. That might not be a very sensible law, okay? But this is actually happening. I can't make this stuff up. Anyway, you've probably, I guess one of these kind of scare slides here. You've probably heard the term climate refugees. Well, all our coastal people, hopefully, eventually will just move inland, or they'll just keep building. But this is Male. This is the capital of the Maldives, and over 300,000 people live on this island within 1.5 meters of sea level. So unlike in the US, if sea level goes up by 2 feet, people are going to move inland, they'll battle it for a while, and then they'll give up, like in Chesapeake Bay, and they'll just give up and move in. Where do they go? They got to find a new country to live in. So these nations are extremely concerned about global warming and sea level rise, and they're all at the United Nations Summit right now, lobbying heavily. And of course, it's not a problem they created or are creating. I mean, their per capita use of fossil fuels wouldn't even be on the charts, right? The United States is the single largest per capita consumer creator of CO2 in the world. Okay, so crap. That's, are we sleepwalking into a climate crisis? Or are these damn scientists just being alarmists? I hear this. I actually heard this from my daughter who's in college when she came home from college and we were talking about climate change in the car. And I go, yeah, we got to be worried about it. She goes, Ma, I just heard that that's not, you don't have to worry about that. It's like, oh, you're killing me. You're killing me. All those years of indoctrination and what are you giving me? So anyways, I'm happy to be the alarm here. I'm happy to be, along with Superstorm Sandy and all the climate scientists, we are your canaries in the coal mine. We have been working on this for decades, and it's not a conspiracy. We enjoy it. We're like people that liked being outdoors and then found geology or, glaciology and realized we could keep working outdoors. Okay, so the point is that everything I've showed you, you can go off and confirm for yourself that it's true, that it's real, and that there's a problem. And then once you do that, you can turn the conversation to what do we do next. But what I'm going to show you next now is I'm going to go a little bit more into my own research and tell you about the little part of the problem that we're, wrestling with lately in the last few years. And I'll start by showing you a picture of the Earth 21,000 years ago at the peak of the last ice age. This is another chestnut I hear a lot, but climate changes naturally. How do we know it's not natural? Well, I hope I made a cause and effect argument earlier that made you think that's probably unlikely to be a coincidence. But the fact is that climate does change naturally. That's why that's why there was a battalion of scientists ready to study climate change, because we have been studying it in the past. So that large ice sheet came down. It was, the margin of it was right about New Jersey. I grew up in Boston. My technician made me this slide. He knows I like the Game of Thrones. So over 4,000 feet was the thickness of the ice sheet over Boston compared to the wall. I could tell by the laughter. You know nothing, Jon Snow. So this is a pretty massive change. In fact, this ice sheet was so massive that when it grew, it dropped sea level by 130 meters. Okay, so that's a big change in sea level. And that ice sheet waxes and wanes. It grows, it decays, it grows, it retreats up to Greenland. And we know why. This is what I cut my teeth on studying. This is my thesis and most of my professional career. We know that the Earth's climate is waxing and waning, warm and cold, because of subtle variations, subtle wobbles in the Earth's orbit around the sun, right? Our climate is set by the amount of solar radiation we receive. And if our orbit, tilts a little bit further away at high latitudes, it's going to get colder up there. If it tilts a little bit more towards the sun, it's going to get warmer up there. And we do not have a perfect orbit around the sun. The masses of Jupiter and Saturn are so great, they perturb our orbit with their gravitational field in a very regular, predictable way that can be calculated by physicists with Newtonian mechanics, et cetera. This is the same reason they can get a lander on Mars. It's very easy to calculate all these things. Not by me, but by other people. So anyways, we know this, and we know that the waxing and waning of ice sheets correlates with these perturbations in the Earth's orbit. And I'll show you another nice little video of a model that I did with Ayaki Awa Oichi, who is the only woman scientist I know in Japan. And so you're looking at 400,000 years ago and present, and we're modeling the waxing and the waning of the ice sheets. It takes a long time to grow an ice sheet. Here it's coming, and very rapid, very quickly you can melt it. I'm going to try to stop this at a key point for you here. Very long, slow growth of the ice sheet, growing all the way down to New Jersey. But the point is that you saw is that it takes a long time to grow an ice sheet, and it's very rapid. You can lose it very quickly. And the reason you lose it very quickly is as it starts to retreat, what is that ice doing? It's so heavy, it depressed Canada underneath it. And so the minute it starts retreating, the ocean flows in to this big hole. And so now you have basically a big chunk of ice that's the warm water is rushing in and melting it from below, from warm water coming in from below. Now, I told you that the sea level was 130 meters lower. How do we know that? This is Tahiti. A very clever scientist named Rick Fairbanks in 1979 had the idea, not at Tahiti, but at Barbados, we can find out how low sea level was by going offshore and drilling down and radiocarbon dating corals till we find the coral that grew at sea level 21,000 years ago. And if you do that, this is a recent expedition to Tahiti. They got beautiful records of corals that basically as sea level rise, they keep up. Corals can keep up. They can grow really fast, and they just track the sea level up 130 meters. And what was amazing about this record was that they were able to show that during the period of most rapid melting of the ice sheet, sea level was rising at a rate of 40 millimeters per year. Compare that to 3 millimeters per year we're measuring now, okay? And that's 4 meters per century. So what's that telling us? That's the geological record telling us that if the climate change is tipping beyond a point it's comfortable at, either because the amount of solar radiation is changing or the atmospheric CO2 is changing, it can respond very quickly. It can cross a threshold. It can cross a tipping point. So here you have a rate of sea level rise that is almost unfathomably fast during its most steepest period, okay? So the argument that sea level can't change by meters per million years, meters per century, sorry, I think you can just put aside. The geologic record tells us it can. Now, okay, 30 minutes. One thing you could think of, well, you know, maybe as you get warmer, it's not the same coming out of a large ice age. And that was one thing we wanted to look at. We wanted to look at, okay, we know how low sea level got, but how high can sea level get when it's warmer than today? Let's look to the past and ask the geologic record to tell us about warmer climate times. Now, I told you CO2 next spring and last spring was 400 parts per million. And CO2 has changed through Earth's history due to changes in the amount of volcanism and seafloor spreading. And we can look back in the geologic record and ask ourselves, well, let's look for a time period when atmospheric CO2 was 400 parts per million and see what the climate looked like. And it turns out you have to go back 3 million years to find that time period. Here is today, here is 5 million years ago. Don't worry too much about what this top record is, but basically Delta 18 in the ocean is an indirect measure of the amount of ice. Here's today, here's 21,000 years ago. That's the 130 meter change. And that record, that model I just showed you, that little movie, it was you watching the ice grow, decay, right? And you can see now, going back in time, you have to go back before 3 million years till you find a period warmer than today. And if you look at the atmospheric CO2 during that time, we have direct measurements in ice cores going back about 800,000 years. That's this black line. And then we have indirect measurements from proxies going back much further in time. And if you go back around 3 million years, the warmest time intervals seem to have a CO2 value of about high 300s, low 400s. And the low values seem to be a little bit higher than today. So the peak warmth during this period seems to be reflective of a world with 400 ppm. And so you ask the question then, and many of us have, how sensitive were the ice sheets to this modest global warming? Small increase in CO2, global temperatures were warmer, there were forests on northern Greenland, all the fauna that lived in the surface ocean was warmer at that time. So we know it was warmer, but what we don't know is how much ice melted. How high was the sea level? If you melted all of Greenland and spread it out evenly around the world's oceans, sea level would rise by 6 meters. If you melted all of the west Antarctic ice sheet, spread it out evenly, sea level would rise another 6 meters. And if you melted all of the east Antarctic ice sheet, that's the big elephant in the room, sea level would rise 55 meters, okay? So the question we had as scientists was how much of this ice melted in the Pliocene? Now, how might you get at that question? Well, this is a modern setting, and these rocks have these very characteristic bioerosional notches. Some think they're eroded by waves, but they're not. These notches are actually created by chitons that just eat away at the rock at the intertidal zone. And you could see, you might come along, and this particular slide is from Barbados, and see this, and you go, oh my goodness, there's a bioerosional notch. Sea level must have been right there at one point in the past. These are more common than you might think. That is a way a geologist might infer where sea level was in the past. Or they might see a long sea cliff. This is an erosional sea cliff with intertidal fossils at the base of this cliff. This is on the Roe Plain of southern Australia. It's 80 meters high at the top and 30 meters at its base, and intertidal sediment right there at the base of this cliff. That was obviously at one point eroded by the sea. Or you might just find yourselves in northwestern Australia overlooking the Ningaloo Reef. This is a long barrier reef off of northwestern Cape Ranges. And you might find yourself hiking inland and standing on a fossil reef. And you know that sea level used to be right there at some point in the past. So these are all the tricks that geologists going out in the field can look for, date, and say, sea level was here, okay? Now, this is a lot of fun. And when I started thinking about this question about 5 years ago, what was sea level in the Pliocene? What really, I went to the first thing you always do is what's in the literature, right? And it turns out that since the late 80s, quite a few studies had been published about what Pliocene sea level was, okay? And this is This is a summary of the published literature. And if you go to the older IPCC reports, they generally just took an average and said sea level was 25 meters higher in the Pliocene, which means all of Greenland's gone, all of West Antarctic ice sheet's gone, and a little bit of the East Antarctic ice sheet's gone. 25 meters higher, climate in equilibrium with 400 parts per million CO2. That's a lot. Okay, but anyways, looking at this, I thought, okay, 25 is about average, but why is there so much variability? Why do some people think sea level was 10 meters higher while other people think it was 25 to 30 meters higher? Okay, so this bugged me. All right, and just this as an aside, the modeling community, the people that are trying to model future warmth, the ice models embedded in the global climate models are the weakest link in these predictive models. Modeling ice is very difficult. It's the final frontier of climate modeling right now. But the modeling community, they really wanted to know how much ice there was, because they're running these experiments where they put 400 ppm in, and they, to create the Pliocene, and their model will say sea level rose by this or sea level rose by that, and they want to know what's the answer. Tell us what the data tells you. So that community really wanted to know what sea level was too. So coming back to this, why was there so much variability in these estimates? And very quickly it became apparent that the reason there was so much variability was because all these studies just thought of the ocean basin as this rock-solid tub that the water just sat in flat. Now, one of the really great things about earth sciences is how interdisciplinary it is. There's geophysicists, there's geochemists, there's geobiologists, there's regular old geologists like myself, and the really cool stuff comes together when these different groups start collaborating. And I happen to know and was collaborating with a geophysicist who was studying modern sea level. And I knew that you just can't assume that the Earth's crust doesn't move. especially over 3 million years, okay? And you can't even assume that the surface of the ocean is flat. Now, I'll show you something that's really going to, like, usually when I show this and explain this, people go, oh, that's so cool. This is why we need scientists, kind of a thing. I said that, and I am a scientist when I learned this. So here is a model that predicts what sea level is around the world when Greenland and West Antarctic ice sheet melt at a rate of 1 millimeter per year. And in fact, that's the best estimate of what is happening right now. And you'd think, great, everywhere the ocean is rising by 1 millimeter per year, okay? But in fact, that's not what's happening. And you can see here that there's places that are rising by 1.1, 1.3 millimeters per year, 30%, 20% higher than it should be. And other places up here around Greenland and around West Antarctica that actually are dropping by 3 millimeters per year, even though sea level's rising because those ice sheets are melting, and you're going, this is a head scratcher. What's going on here? And the reason is because these ice sheets are so massive and on top of the Earth's crust that they're actually exerting a gravitational attraction on the ocean. They're pulling the ocean towards it. So you can melt Greenland and be standing on the shore of Greenland, and instead of watching the sea level rise, you watch it fall away because you've decreased the mass of the Greenland ice sheet. And if you melt all of Greenland, sea level rises globally averaged by about 6 meters, but right near Greenland, and then decaying away over about 500 to 1,000 kilometers. But right near Greenland, sea level will drop by many tens of meters. So the ocean is a fluid, and it's attracted by mountains. A student earlier today was telling me how sea level in from San Francisco Bay is higher than at the mouth of the bay because it's being pulled up by the Sierra Nevada mountains. So this is a really tricky thing. So you can imagine the scientists that are out there making predictions about how sea level is going to change in Florida or Washington, D.C. Might have to incorporate all this in there, and they do. They do incorporate that. But these Pliocene people didn't. So here's another thing, completely separate, that's also really cool. Here's the ice sheet from the last ice age, plop right there on the middle of Canada. It's so heavy, it depresses the crust, and the deep material deep within the crust and the mantle flows away, okay? So the crust is viscous and it deforms. But what happens when you remove that ice sheet quickly? Well, all through the Holocene, Hudson Bay area has been rebounding, but it's not an instantaneous response. It's a long, slow, viscous response of the mantle, okay? And you can radiocarbon date these shorelines, and you can see they're just slowly coming out as the crust rebounds, right? So if you're standing in Hudson Bay and you're right there, you think sea level's falling with time, okay? But what about the rest of the world? The crust pushed down over Canada, but it bowed it up in this area around here. It's just like, imagine like a large waterbed. You lie in the middle and the outsides go up, right? So now you've taken away this ice load, this is coming up, and this area, the bulge, is going back down. So if let's say you're in Bermuda, right? Right there in the middle of this peripheral bulge, it looks like sea level is rising because that bulge is subsiding. And you have to add that sea level rise on top of the climate-caused sea level rise from thermal expansion and ice melt. So so really, all I'm trying to get you to see here is there's this beautiful complex dance of sea level going on with all these factors happening at the same time, and you have to tease out the 1 millimeter per year that's being driven by climate change on top of all these other little things. So I think I might jump ahead a little bit here. I have to log in to see my timer. Yeah, I'm gonna jump ahead a little bit here, because it's coming up on 43 minutes. And I had that long introduction, ate into my time. It reminded me of, you said the Discover magazine, 50 important women in science. We used to joke that back in the early 2000s, they probably had trouble finding 50 women in science. Things have changed a lot in 10 years, actually. Okay, so I'm just going to kind of wrap you up on my part of this research. So what we're doing is we're really struggling with this Pliocene question. But now we're going back to all these sites, and we figured out how to make the corrections. How do we correct these sites? Because, for instance, our site in Australia, that Paleo sea cliff I showed you, our isostatic rebound modeling would say that if that shoreline in this particular experiment, we assumed sea level was 14 meters higher 3 million years ago. And our modeling says that that shoreline would be at 8 meters today because of this deformation of the crust by the current ice sheets that's going on. So we need to add 6 meters to our field data. Now I'm going to make a long story short, and we thought, oh my God, this is so cool. We figured out how to correct these ancient shorelines for crustal movements. We're going to correct all the data, and it's going to come magically into a line, and we're going to know what sea level was in the Pliocene. That paradox of this huge variability in the data. That did not happen. We had a little less variability, but we still had a lot of variability. And more importantly, we had shorelines like this one on the east coast of the US. This is called the Orangeburg Scarp. It's an ancient 3 million year shoreline. And it is this, again, you're oriented, this is the shoreline, you're oriented going along there. And this shoreline, even after you correct for isostasy, it's still 50 meters higher up around Virginia than it is down in Georgia. This was a real head scratcher. And what we discovered, basically, in a nutshell, was dynamic topography, which was this kind of mythical beast within the earth science community, which is changes in elevation of the land driven not by plate tectonics colliding with each other, but driven by buoyancy forces deep in the mantle, pushing up the crust from below. So we actually have found something that a whole other area of the earth sciences had been modeling for years. We found the physical evidence of the fact that under New Jersey, there's actually deep-seated forces deep within the mantle pushing up New Jersey. Now, where does that all take us? We're now having to model mantle dynamics to get at sea level changes 3 million years ago, which is a lot of fun, but we're still far from being able to say this is how high sea level was in the Pliocene, but we're having fun getting there. Okay, so now I'm going to end with 2 more slides. And I like the New York Times crossword puzzle. I like Ken-Kens. I like doing puzzles. I like words. I love this word. I learned this word about 5 years ago. And the definition of usufruct is the temporary legal right to the use and enjoyment of the property of another without changing the character of a property. So I might say you can use my apple orchard, just don't use the trees for firewood, kind of a thing, right? But anyway, here's the use. I found an example of the use of usufruct in a sentence. And I'll read this. Bear with me while I read this. The question whether one generation of men has a right to bind another seems never to have been started either on this or our side of the water. Yet it is a question of such consequences as not only to merit decision, but place also among the fundamental principles of every government. I set out on this ground, which I suppose to be self-evident, as a clue, that the earth belongs in usufruct to the living, that the dead have neither powers nor rights over it. And I think what he's saying here is that I can't screw it up for you and your children, okay? And this was written in a letter by Thomas Jefferson to James Madison in 1789, which leads me to my last slide, which kind of puts everything back on you. And everybody's got to come to a personal philosophy on global warming at this point. It's not a scientific question anymore in my mind. Although there's plenty of interesting scientific questions embedded in global warming, the basic facts are clear at this point. This is just one of many efforts, grassroots efforts. There actually was a group of teenagers that brought suit in the federal government in DC that was the government's duty to protect the earth and maintain a stable climate for their future and the future of their children. In fact, over the summer, the case was dismissed, and they said that the issue of the public trust and who's responsible for the public trust was essentially a states' right issue. So I'm sure this will go back to the states, and I'm sure, I think this is going through places like California and Vermont now. But, I just want to end by saying, this is something we all need to think about. The decisions, even though the decisions we make now impact what happens 50 years from now. If we make smart decisions now, less destructive things will happen 50, 100, 200, 300 years from now. If we let the corporations and the energy corporations, and not all, but if we just left it to the corporate sector to make the decisions for us, it's just going to be business as usual. Short-term profits, it's almost their duty, to shareholders, right? It's not true of every corporation, but nothing will happen. Things are only happening when people at the grassroots are demanding it of their politicians and their governments. So I will leave it right there. I will say thank you. There's many places that you can go and find information about all of these issues. And I just hope everybody thinks about this and does something. Thank you. Just ask that if the land is rebounding when the ice sheet's removed from it, can that kind of unload the crust and lead to more volcanism? And that idea is very topical right now. A cruise just went out, an NSF-funded cruise was just out in the Northwest Pacific, trying to take cores very close to mid-ocean ridges and volcanic regions to try to see if there was a glacial, interglacial volcanism signal in the core. So, and it would be through kind of glacial unloading, which would depressurize, for instance, a magma chamber and make it more likely that magma could escape. And it could be, that could be a feedback then on climate because that would release CO2 gases. And also volcanism, if there's a lot of sulfate aerosols, can cool the climate.
There's something called the rule against perpetuities in the law.
Uh-oh, got a law question.
And that means you can't leave something to somebody who's more than a life being in 21 years. Mm-hmm. That's why we think the way we do, because it won't affect us in our lifetimes or our children's lifetimes. And the law says you cannot even leave an inheritance to somebody
Beyond 21 years?
A life in being plus 21 years.
Okay, well, I've got an interesting law insight. I'm not sure I can repeat it properly, but the competing law to usufruct is you can't leave something to somebody beyond a lifetime in 21 years. But, I mean, can you get through that by just stepping through your generations?
They're moving around that to some degree, but the concept is we cannot be concerned with people who we cannot possibly know.
That's a useful concept if you are Exxon.
That's what they do.
I believe it. I believe it.
Politicians do. They cannot be concerned beyond that.
I believe it. I mean, we're at a unique point in history, in human history. It is true. What we do now no longer is just the Superfund site. It's the whole world.
I'm hearing from climate deniers that there's actual new glaciation in the Antarctic.
New glaciation?
Is there anything to that at all?
Well, I mean, not in West Antarctica, but East Antarctica is kind of the big variable, right? And I was talking to the students earlier, we were talking about this. So Antarctica is extremely cold and dry right now. It's so cold, there's almost no moisture in the air, far, far below freezing. And so you could imagine a very intuitive argument that if it got warmer, the air would hold more moisture, you'd have more snowfall, and the East Antarctic ice sheet would expand. And that models show that. And so that is why there's always been this view that the East Antarctic ice sheet will be very stable, and so it'd be impossible to get a 20-meter sea level rise over centuries to millennia. And then there's the counter view that the East Antarctic ice sheet also grows out over the ocean, and so if you bring warm water up under it, water that's been warming for centuries or a century, it will melt it from below. So you have these two, like the collapse of the Larsen B ice shelf. When that ice shelf collapsed, all the ice streams stopped being buttressed by the ice shelf and started flowing faster into the ocean. So you do have those two competing effects, and I can't say there's an answer. But it's easy to say that will save us, but we don't know that. So, and in fact, the mass balance on East Antarctica is very uncertain. It might be a little positive, it might be a little negative. It seems to, it's not certain right now. It's not obviously growing. Next. Go ahead.
Can you say whether carbon dioxide precedes the glacial cycle or follows the glacial? Do we know enough about that yet to say, is it simultaneous? Or
Yeah.
is it one affecting the other or the other way? Can we say that yet?
Yeah, a nice paper was written. A lot of papers have been written that. I'll tell you why it's hard to say that. Because you look at the ice core and it tells you, you can measure temperature in the air over Antarctica by looking at the deuterium-hydrogen ratio of the water. And so you can see you're down in the glacial, and then you can see it beginning to warm, okay? And then you want to see, well, does the CO2 go first or next? But the problem is the CO2 is measured in an air bubble trapped in the ice matrix, right? And imagine I'm standing on the snowpack and the temperature changes right now. So that temperature change will be recorded on the snow I'm standing on, but the CO2 at the same time is just now being encapsulated in a bubble probably about 4 feet down in the fern, right? Because it has to be sealed off, so it's happening at depth. And that getting exactly, I'm trying to make you see the beauty of the problem. Trying to understand exactly that offset is really tricky. But here's what I know. I know that the climate is changing because the orbit's changing, right? There's no way the orbit is being a slave to the CO2. And as soon as that orbit changes, ocean circulation and productivity around Antarctica changes. And that is what controls the CO2 in the atmosphere. The atmospheric CO2 changes on glacial and interglacial timescales because ocean productivity can breathe CO2 in and out of the deep ocean, the same way you saw the biosphere breathing CO2 in and out on annual cycle. If you increase productivity in the ocean, which you do during glacials, which I can go into all the reasons why, you suck more CO2 out of the atmosphere and put it in the deep ocean. So it's a strong positive feedback on the climate system. You get colder, productivity increases, CO2 in the atmosphere drops, that makes it even colder, and it goes the opposite way on the warming side. You had a question?
You mentioned earlier that we're not running out of fossil fuels anytime soon, yet current rates of data show that we're past peak oil. Do you think that as we fight for scraps and our current rates of consumption go up, that we'd be pushing ourselves past the worst case scenario that's been projected by climate models?
I think there's two questions there, but yeah, I think that massive reserves of fossil fuels have been found over the last few decades, and especially things like tar sands and fracking and all this stuff. Some natural gas are less destructive than coal, for instance, in terms of CO2 and this. But we have more than enough known reserves to take us to 900 ppm if we choose to go down that route and burn, frack, mine, tar sand, all that fuel.
So you mentioned like the orbital and the angle of the Earth itself, like the connections between the Earth and the Sun is influence the climate in our planet. But what's the influence of the Sun activity?
So that's a really good question. We started measuring the solar constant, you think in the 60s, and there's 11-year variation in the solar constant that's tiny, 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 tiny.
I have heard some articles that talk about like the Sun itself has a big circle, more bigger than the 11 circles itself, like something called the grand minimum of the Sun activities. Like maybe one day the solar radiation's intense is lower.
Yep, that is true. There was a minimum in sunspots that lasted a long time, completely inexplicable. And it does correlate with the Little Ice Age, a period of colder climate in Northern Europe. But again,
So at that time, we all assumed to be a saver gas.
yeah, I mean, if you look at, the last few decades in the 20th century, regular sunspot cycles, and now we know the change in solar variation associated with those sunspot cycles, I'm not going to say people haven't tried to find some mechanism to make the sun control what we're seeing and what I showed you. And I would say that nobody's been able to do that in any convincing manner to, the satisfaction of your average climate scientist.
With rising CO2 levels and temperature levels, do you think in about like 5,000 to 10,000 years that the Earth would be uninhabitable for humans if it continued?
That's a really great question. So the question was, with rising CO2 levels, and I assume kind of maybe what you mean, if we let it rise forever, would the Earth eventually become uninhabitable for humans? And I'll say that this is like another question I'm sometimes asked, which is, when is there going to be the next ice age? And my answer to that is that I don't think there's ever going to be another ice age while humans are on the planet, because we understand how to control climate right now. We're doing a very bad, bunged up job of it, but theoretically we know how to do it, right? So theoretically, we're going to figure out efficient ways to remove CO2 from the atmosphere, bring down the temperatures, over centuries, and titrate the atmosphere so it's a nice climate we like. Now, I'll tell you that, we will, if the orbit starts changing so that the ice sheets are creeping down over Canada, we'll just pump up the CO2 and keep everything the way it is, the way we like it. Russia would love it if it got warmer. They are very quiet. They just sit there at the back like the Cheshire Cat. Climate gets 2 degrees warmer globally. Russia's the big winner. They got the Arctic, massive amounts of fossil fuels, shipping lanes. In fact, before it became really politically incorrect, Russian climate scientists used to come to meetings like the American Geophysical Union meeting back in the 80s and say, it's moral imperative for us to increase CO2 and warm the globe so Russia can become the breadbasket of the world. There will be no more starvation. They would say that. So anyways, that was a long answer. Long before that Earth would become uninhabitable, we would fix it so it was just the way we wanted it. Of course, the whole bugbear here is that if we don't get around to doing it right soon, we get a world with a sea level that's, 1, 2, 3, 4, 5, 10 meters higher. That's a very different world. And there's a lot of chaos dealing with that. And that's over centuries.
If you had to roughly estimate a time that if, say tomorrow, all of a sudden, all the fossil fuels stop getting burned and all of the human presence
Yep.
of CO2 producing into the atmosphere stop, how long would it take for the Earth to like bring
Equilibrate.
itself back to
Yeah.
what it would be normally?
That's a really great question. I have colleagues who work on exactly that. One thing you often hear about global warming is that even if we stop right now, there's still warming in the pipeline. And it's true. The surface ocean has been absorbing heat for 100 years. It circulates. It's going to bring that heat up to the poles. It will interact with the ice sheets it sees at Antarctica. So, there's always kind of this idea that the climate will keep going up, but then probably if we stop right now in the late 20th century, it'd probably peak and start turning down again. And that comes back to this question of why is it so critical that we do something now? Because every decade, let's say, and I've been at this for 3 decades, and the writing's been on the wall for 3 decades. Every decade you put off any serious action on climate change, it just pushes it down the road. The sea levels get a little higher, and it pushes it down the road. And the other kind of bugbear about all this is you never know if you're going to pass a tipping point. Like if all of a sudden the entire West Antarctic ice sheet goes unstable and just starts to melt, and you can't bring it back because it's gonna float off its grounding lines, and the whole archipelago will fall apart and sea level rises by 5 meters over 300 years. There are actually scientists that think the Pine Island Glacier has already passed the tipping point. This is just one of many glaciers around Antarctica. So I personally believe, knowing what I know, that it's really important that the world get its act together in the next decade, next 2 decades at the latest, or things really are going to be, things are already very bad. I think the insurance agencies will drive us there because they're going to get tired of paying out the huge payouts, right? But really, what's going to happen is that it has to be from the people, right? It's going to go up. The politicians are only going to listen to the corporations unless the people demand change.
I'm a biologist, so it seems to me the only living thing we've talked about today is man. And
How about my coral reefs I was standing on?
in terms of all these changes and all the sea level rise and shifting habitats in what used to be the Soviet Union, how crazy is it going to get biologically?
Well, I have some great friends, the Barnowskis, that work at Stanford and Berkeley, and they study the whole global warming problem strictly from the perspective of ecologists. And, it's not something I can speak knowledgeably about, but, the ecosystems are already suffering. Things that, migrated with the first, frost of this are now showing up 2 weeks later, and the thing that needed them to pollinate them 2 weeks earlier then, fall apart. This ecosystem evolved over millions of years, thousands of years to work together the way it does, and it's kind of falling apart at the seams in terms of extinctions and stresses on ecosystems. So I can't really tell you much, I'm afraid. The big one I know about is ocean acidification, right? 50% of the CO2 we put in the atmosphere is going in the surface ocean. It's measurable, we see it, and it's acidifying the ocean. And there are concerns that if it continues to do this, it creates stressors on coral reef systems, marine invertebrates. Oh, I can't see anything up there. You guys could have been on Mars for all I knew. Really, I'm like blind up there.
My name is Vincent Obadi, and I think that was a very wonderful presentation.
Thank you, Vincent.
I realized that at each of your short stops within the presentation, you mentioned that we need to do something about climate change.
Yes.
Would you consider carbon trading as one of the options?
Oh.
Do you think that there are some myths that
Yeah.
And I also realized, just as an added question, short question, I also realized that we have more focus on carbon, yet we are aware that there are other greenhouse gases, like nitrogen, for example, which is actually 78% in the atmosphere.
Yeah, nitrogen is not a greenhouse gas, but maybe you're thinking about methane.
Methane, yes.
Yeah.
Methane and, should I say water vapor?
Yeah, well, I mean, the water vapor is always there. Water vapor, it gets warmer. I mean, the water vapor's there. I guess the question with the water vapor is what will it do to clouds? And if you had certain kinds of clouds have a higher reflectivity and so could reflect sun. So for decades, there's been this, hope within the community that it would be a perfect negative feedback to counteract increasing CO2. But you look at the geologic record and that's not what you see. The methane question, yes, methane is a very powerful greenhouse gas, and it also has been increasing dramatically in the atmosphere through agricultural activities. However, methane is measured in parts per billion, not parts per million, and it has an extremely short lifetime, like a decade, and it breaks down to carbon dioxide, and that carbon dioxide is in parts per billion, not parts per million. So nobody should care about methane. CO2, the parts per million, input is the big problem.
Yes, and what is your opinion about the carbon?
Oh, I can't even say anything about carbon trading. I just don't know enough about it. I'll tell you about another cool study that I read. It was in PNAS, the Proceedings of the National Academy of Sciences, last month, and I came to my attention because the lead author came to Lamont and gave a talk, and it was fascinating. It was about the carbon load associated with the food choices we make. And so, this has always been one of these things that, like, eating beef versus a vegetarian diet. I mean, our food and agriculture is a huge part of the CO2 load we put per capita into the atmosphere in the United States. And we have a very dispersed food chain that requires a lot of energy to get it to us and grow it. And here was the result of this study. It was so cool. They compared how much energy it takes from start to finish, from the farm through the gate to your table, to provide 1,500 kilocalories of beef, pork, poultry, egg, or legumes, right? And what was amazing to me was that pork and chicken were only slightly worse than an egg, which is only slightly worse than a legume, but beef was about an order of magnitude, actually almost 2 orders of magnitude, more energy intensive to get you those same calories. I haven't had beef since I had heard that talk, and I haven't missed it. I had great chicken meatballs last night. You think, how could that be? Why would it be how could it be an order of magnitude worse than a pig? And, he walked us all through the data, and it was really interesting because, imagine it, you have a pig, and that pig gets pregnant, and it has a really short gestational period, and it gives you 15 piglets, and they're fully grown within, a few weeks. And then you have a cow, and it has a really long gestational period, and it has 1.5 cows on average, and then you have to raise those cows, and it takes 3 times longer. And so all these things, they went through every step, and it turns out that beef is just a huge source of greenhouse gases. So think of that every time you go to McDonald's.
About 2 weeks ago, a science writer named Matt Ridley wrote an article in the Wall Street Journal about all the models being wrong because for 15 years there's been no climate temperature rise.
Yeah.
Was he just looking at too short a period there, or what's your take on it?
I actually have the data right here. That's a great question. It hasn't been 15 years. It's been more like 10 years. And believe it or not, I've seen now 3 or 4 talks about this at Lamont because it's a big puzzle we're all worried about. So I don't know where I don't know where I put my pointer. I think I lost that. Sorry. This is, here's the, this is really squashed now, y-axis. Here's 1880s to about today. And you can see here's the rise in temperature. And right there from a number of different groups. And you can see it's flattened out in the last decade. And so people point to this and go, see, global warming's over, okay? And yeah, okay, it's flattened out. But, the CO2 is still rising, and right here, it's just last few years, this trend has kind of flattened out. So if you looked at the last 10 years, you'd say no global warming. Oh, it's okay, thanks. And so, this is a hot topic right now. So people are like, I heard one talk that said, well, we do know that volcanism controls climate. If you have a big eruption, Penatuba, I think it was 92, that couple year cooling right there, that was Penatuba. Volcanism cools the climate because it blocks out sun from sulfates. One scientist came and said, what the models haven't been including is low-level volcanism from Southeast Asia, which apparently has been unusually high, and that these sulfates are enough to cool climate. So a random kind of statistical perturbation in the amount of volcanism. Another person thinks that it has something to do with not interpreting the Arctic data right. I read that one, I didn't see the talk. Another person said that this has to do with the transfer of heat between the tropics and the North Pacific, that heat is going into the ocean and that it's not in the atmosphere right now. So this is here's the question. This is a very active research right now. I mean, there are lots of groups working on this, trying to figure out where's the heat. The heat has to be there. The CO2's been going up. So where'd the heat go? Is it counteracted by volcanism? Is it going into the ocean preferentially? Does it have something to do with warming in the Arctic? My favorite answer is it's probably all of the above, all of the above. But, we will know. I seriously doubt in 10 more years this is going to still be flat. That would be really almost baffling.
I was told that with all the ice melting and stuff, that there could be a chance that the ocean conveyor belts could ever shut down.
Yeah.
Is there opinion on that?
Yep, that's a really good question. I've spent a lot of time studying the circulation in the North Atlantic. And the ocean circulation is very sensitive to the distribution of heat and moisture at the surface. And so there are times during the Ice Age when we see these huge breakouts of glaciers and of icebergs, and we see it because we see the evidence of the material that the icebergs dropped in the sediment. And when those happen, the conveyor belt does look like it shuts down, and probably because there's this huge thick layer of meltwater, fresh water, which is less dense on the surface that stratifies it. The models, that said, the models, at the rate that the Greenland ice sheet is melting, the models don't predict that will happen. But it has happened in the past.
I think, Dr. Raymo, I know you promised you'd stay as long as there were questions, but I think we have to be fair to you because I think the questions are going to be unending. I'd like us all to thank Dr. Raymo one more time.
Thank you. Thank you.